Hello. So how do we differentiate a logarithm function that is not to the base of e? That is to say, not an actual log. By the way, when I use the word log or logarithm, log is short for logarithm, obviously. It's a lot easier to say log. So I'll be using that term from now on. So when I say by natural log, obviously I mean it's not to another base, it's to the base of e, not to the base of say 10 or 2. And the question here really is, why am I saying this, why am I asking this question? And it's because when we're doing differentiation, when we're trying to find the derivative, we can only find the derivative of a natural log. So what would we do if we had to find the derivative of another base, like base 10? And here's a classic example below. We've got the formula for the gain of an amplifier. So the G for gain equals 20 times the log of 3V. So that's a proper formula. The bit in the brackets would be the gain in voltage divided by the input voltage. And this is just another way of looking at it. So basically what we're saying is the input voltage V has been amplified by 3 times. And this is the typical formula for working out the power and then converting it into decimals. Anyway, I'm not going to go into that in any more detail, just to let you know it is a proper equation that's used in electrical engineering, particularly electronics. Okay, so how do we do it? Well, it turns out the solution's quite simple, and it's a bit similar really to when we're doing different derivatives of trigonometry functions, such as sine or cos. We have to work in radians, and if you have your numbers that are in degrees, then the simple solution is to convert it to gradients. And the simple solution when working in logs to other bases like base 10, straightforward, just convert it into a base of e. And as it turns out, there's a formula for that. Before we get into that, I just want to digress slightly. Okay, as you're probably aware that the derivative of log x is simply 1 over x. Now I just want to do a slight digress here because it's going to be relevant when we do our solution to our problem. What do we get if we've got a constant in front of the variable term x? So for example, we've got here y equals log to the 2x. What's the solution to that? Well, as it says there, you may be surprised to learn that the solution is very simple. It's just 1 over x. The 2 disappears. It's the same answer. In fact, it doesn't matter whatever the constant may be, you'll still get 1 over x. So if instead of 2 it had been 2 billion, we'd still end up with 1 over x. And the question there is why. And if you know the answer to this, you can skip this part of the video and get onto the examples of doing the conversion of logs to other bases into natural logs to do a derivative. But I'll just quickly go through this. There's 2 ways of looking at it. Well, there's possibly more ways of looking at it, but there's 2 ways of solving this. To see why it ends up as being 1 over x when there's a constant in front. And the easy way is probably this one, which is to say, I'm going to show you both ways quickly. So for example, we know that we've got so log of 2x. So if I just take a page down, here we've got the log laws, and in this one I'm going to use this one, which you're probably hopefully familiar with. So we've got if log of m times n can be rewritten is identical to log m plus log n. Okay, so we're going to make use of that in this example. So in other words, I can go split it up like this. So that's identical. Okay, and would give an identical answer if you was to do that under normal circumstances. Now if I do the derivative of this, okay, what we've got here, we've got a constant there. So any constant, that means anything without an x. Okay, it doesn't have to be a number, it can be a letter, but anything without an x disappears. So that basically is 0. And normally we don't write in the 0, we just ignore it. But to make it more explicit, I'll put it in this time. Right, and as you know, the derivative of log of x is 1 over x. So there you go, there's the simple way of doing it. It's one way of doing it. And as you can see, if this was 2 billion, you'd still get the same answer because it'd still be a constant. Okay, if I just scroll up a little bit to give myself a bit of space, that's the easier, quicker way of doing it. Another way of doing it would be to use the chain rule. So with the chain rule, what we would do is we would say, whoop, let's put my pen back on. User error. Use the chain rule. So we let u equal, so we're going to substitute in, so we're going to let u equal 2x. That means that therefore we've now got y equals log of u. Now the derivative of that, I'm not going into the chain rule now, of course. I've done another video on that if you're not sure what it is, but you need to know how to do it. It's very useful in finding derivatives. Anyway, so we get dy over du gives us simply 1 over u, as expected, and the du over dx simply gives us 2. Okay, right, so if I then go bring these together as per the formula for the chain rule, I get 1 times u times 2, or bring them together, 2 over u. Now u obviously doesn't have any sense in this because we're talking in terms of x, so then we have to solve it, we have to substitute back in, so we're going to get 2 over 2x. Okay, 2 divided by 2 cancels down to 1 over x. So that's the longer way of doing it, but it proves the other method. It's a proof, so it's good. Okay, so keep that in mind. Right, so onto our next solution. How do we solve our one? Let's just go down a page. Let's start with a simple example. So we're going to solve y to the log base 10 of x. Now, as you're probably aware, if you've got a calculator, you've got 2 buttons on there for logs. You may have a third one that allows you to change the base, but generally you've got the 2, and you've got log L or G, and by convention that normally means log to the base of 10. The other one is ln, and that's your natural logs. That's to a base of e. Remember that e equals 2.718. Whoop. Why does my pen not want to work now? That's curious. Thank you. 18. And you can be really clever. Go to 2 more decimal places. A little trick for you here. You'll notice 1828. If you repeat that number, I'm digressing again, but it's a little party trick for you. 1828. And another little party trick, you can go further, because if you think of a right angle triangle that's got 2 equal angles, you've got 4, 5, 9, 0, 4, 5. If you just write that out with any explanation, people can think you're really clever. Okay, obviously I'm not clever. Right, so we're going to solve this by using this law here. Whoops, the law for changing. Get rid of that. So that one there. Okay, so what it says is if you've got it to one base, you want to convert it to another base, you do your new base with a log of the x, whatever the x may be, divided by the log of that new base, but with the old base in as your x term. Okay, so it's quite straightforward as it turns out. Obviously it involves a bit more work if you want to differentiate, but let's have a look. So we can change this, so we can now say that y now equals, so changing it to our new base, so I'll, just for clarity, I'll write it like this. Divide by so the old base was 10, so we put 10 in there. Okay, and a more conventional way of writing it is like this. When we get there, whoops. Okay, which can be written like this. Of course. Okay, so 1 over log 10 times log of x. Now if I want to do the derivative of that, this term here is just a coefficient in front. So it's linked to it. I didn't have to have the times sign in there. So if I do the derivative, dy dx, so this just stays as a in front as a value. It's just a number at the end of the day. Okay, and the derivative of log of x, as you all know by now, is 1 over x. So basically that's the solution. If you do the bit of maths, 1 over log of 10, apparently it would give you 0.4, and you don't need to do this. 43429 if you want to go to enough decimal places. Okay, and that's divided by x. Okay, so that'd be your final solution. Final, except there's more decimal places than that. It could be an irrational number for all we know. It could go on forever. Okay, so that's that. So it's, as you can see, it's fairly straightforward. Okay, now what about our example? Okay, so this time we're looking for, we need to do some conversion first, and then we're going to do dg over dv, where v is a variable, which is the voltage, input voltage of the amplifier. So we need to split it up, so we need to rewrite it. So g will equal, so 20, we'll take this outside, bracket, put it in brackets, put it outside brackets. So we've got, so natural log of 3v divided by log base 10. It incidentally is base 10 when you're working with amplifiers. Well, it's when you convert into decimals. That's where the term comes from. So this is going to be to 10. Incidentally, I digress again, but it sounds in decibels as well. It's the same principle. Should be a longer bracket there. Okay, right, a bit messy. Okay, so as we know from our previous example, this 3 will disappear when we do the derivative of it, and this will come out front. So what we've got, dg dv, so the derivative of that, so we've got, I'll leave the 20 outside in bracket of the brackets. So we've got, so the derivative of log of 3v, sorry, I need to, this is a constant in front of this, so I need to bring this to the front. It's just a number, remember. Okay, and the derivative of log of 3v is simply 1 over v. Didn't particularly need the brackets, but it never hurts to put brackets in, as long as they're in the right place. So if I do the number crunching, 20 divided by log 10, I end up with 8.686 divided by v. And there you go, that's the solution. So if you get asked that question, how do you do something with a log that's not to base e, you now know it's fairly straightforward. This one was a little bit more of a tricky example with the 20 in front. The 3v, the 3 in front of the v made it a little bit trickier, but as you can see, it turned out to be quite simple in the end. Remember, difficult problems can be broken down into smaller problems that are easier to solve. Okay, thank you for listening.